let's solve some previous year GIT problems from the subject machine design, and the chapter is static and dynamic loading. The first question is, in a structure subjected to fatigue loading, the minimum and maximum stresses developed in the cycle are 200 megapascal and 400 megapascal respectively. The value of stress amplitude in megapascal is, okay, so the stress amplitude or the variable stress is equal to maximum stress minus minimum stress upon 2. Okay, so the maximum stress is also given and the minimum stress is also given, so 400 minus 200 upon 2, 200 by 2, that is 100 megapascal. Okay, so 100 is our answer. Okay, next question. I think let me change the color. Yeah, now this is black, pitch black. Okay, the next question is, a rotating steel shaft is supported at the ends. Okay, the steel shaft is rotating. It is subjected to a point load at the center. Cool. The maximum bending stress developed is 100 megapascal. If the yield, ultimate and corrected endurance strength of the shaft is, the data is given. The yield strength is 300 megapascal, ultimate is 500 and corrected endurance strength is 200 megapascal. Then the factor of so the factor of safety for the shaft is, okay, so you have to find N. Okay, now this is a rotating steel shaft. Okay, and as it is a rotating steel shaft, so therefore it is subjected to an alternating bending stress. Okay, because of this rotation, it is subjected to alternating bending stresses. Okay, that means the upper and the lower fibers above and below neutral axis will be subjected to repeated tension and compression. So that implies if maximum bending stress sigma max is equal to 100 megapascal, the minimum bending stress will be minus 100 megapascal. Okay, now we have to use which theory? That is not given, because when it is subjected to the fluctuating load, when a material is subjected to a fluctuating load with the same values of maximum and minimum stresses, the Goodman's theory and the Soderberg's theory give the same result. How? Let's see. According to Goodman's theory, the formula is sigma mean upon sigma ut, that is ultimate tensile strength, plus sigma v, that is variable, and this is corrected endurance strength, is equal to 1 by n. Okay, and according to Soderberg's theory, this will be sigma mean there is one change here, it is yield strength plus sigma v by sigma endurance is equal to 1 by n. So if it is a rotating shaft, and that implies it is subjected to fluctuating load, sigma maximum is equal to 100 megapascal, sigma minimum is equal to minus 100 megapascal. You see that sigma mean is 0. 100 plus of minus 100 by 2, that is 0. So this term gets cancelled out, this term gets, it doesn't get cancelled out, it becomes 0. So this term becomes 0, this term also becomes 0, and we see the equation is same for both Goodman and Soderberg in this case. So the answer will be, you have to find a variable stress. Sigma v is equal to 100 minus of minus 100 upon 2, that is 200 by 2, that is 100 megapascal. Okay, and the corrected endurance stress is given as 200 megapascal. So 100 upon 200 is equal to 1 by n, and n is equal to 2. So the factor of safety for the shaft is 2. Next question. For the given fluctuating fatigue load, the values of stress amplitude and stress ratio are respectively. Okay, so the value of stress amplitude and the stress ratio you have to find. Okay, so this question, stress amplitude was you have to find the stress amplitude in question number 1, which I've done in this video. So stress amplitude is equal to variable stress, which is equal to maximum stress minus minimum stress upon 2, and maximum stress from this graph is 250 megapascal, and minimum stress is 50 megapascal. So that implies 250 minus 50, 200 divided by 2, that is 100 megapascal. So stress amplitude becomes 100, so B is not the option and D is not the option. The stress ratio, we know the formula of stress ratio is equal to sigma minimum upon sigma maximum. It is the ratio of minimum stress to maximum stress. So this is 50 upon 250, and this becomes 0.2. Okay, so the answer will be 100 and 0.2, which is option C. Okay, let's move on to the next question. A machine element has an ultimate strength sigma u of 600 Newton per mm square, 600 megapascal, and endurance limit of 250 megapascal. The fatigue curve for the element on a log plot is shown below. Very important line. Most of the students will miss this log part. Log graph. This is a log graph. Okay, so this value, this A is actually log of 0.8 sigma u. Okay, this sigma en here is log of sigma en, that is endurance strength. This is also log. Okay, so whatever values you have to take while solving the question, you will have to take it with log, and this is log to the base 10. Okay, so let's read the question. Oh, I guess this is an incomplete question, so I'll read the complete question for you. So it says that if the element is designed for a finite of 10,000 cycles, that is for 10 raised to the power 4 cycles, if it is designed for a finite of 10 raised to the power 4 cycles, the maximum amplitude of a completely reversed operating stress is. Okay, so for 10 raised to the power 4 cycles, you have to find the amplitude, the maximum amplitude of a completely reversed stress is. So 10 raised to the power 3 number of cycles are here, 10 raised to the power 6 number of cycles are here, so 10 raised to the power 4 number of cycles must be somewhere here. Okay, this question can it is solved by the basic concept of similar triangles. So let this stress that we have to find, let it be sigma. Okay, so actually it will be log sigma. Okay, whenever when we'll be using this value, it will be with log. Okay, so let's take this smaller triangle and this bigger triangle, so these are similar triangles. Okay, let this point be C and this point be D, this be E. Okay, so AC upon AE will be equal to, let this point be F, is equal to this is CD upon this is EB. Okay, so AC upon AE is equal to CD upon EB by similar triangles. Okay, so this becomes log to the base 10, 0.8 into the ultimate strength, which is 600. So this value is 480 megapascal. Okay, so log 10 of 480 minus log sigma upon what is AE. AE is log 480 to the base 10 minus log this endurance limit is 250 megapascal, so this will be 250 is equal to CD. CD is 10 raised to the power 4 minus 10 raised to the power 3, but these values are also with log. Okay, so this will be log 10 raised to the power 4 minus log 10 raised to the power 3 upon EB is log 10 raised to the power 6 minus log of 10 raised to the power 3. Okay, so all you have to do is solve this equation and you will get sigma. So this is 2.6812 minus log sigma upon the difference is the difference of this value is 0.2833. Just match the values if you solve this question. This is 4 minus 1 upon 6 minus 3, that is 1 by 3. Okay, so on further solving you will get 8.0436 minus 3 log sigma cross multiply is equal to 0.2833. So solve this, you will get sigma in terms of megapascal only, and that will be equal to 386.159 megapascal. You'll directly get it in megapascal because you have put the value here in megapascals only. Okay, so this is our answer, 386.159 megapascal. Check the units before putting the value, and that is, we have to put the value in megapascal, so this is our answer. Okay, let's move on to the next question. A machine component made of a ductile material is subjected to a variable loading with this is minimum stress minus 50 megapascal, maximum is 50 megapascal. Okay, so if the corrected endurance limit and yield strength for the material are given respectively, the factor of safety is. Okay, so the machine component is made of ductile material, and for ductile material we use Soderbergh's theory. And although for reverse loading, as I have told you earlier, that for reverse loading Soderbergh and Goodman's theory gives same results, because that sigma mean upon that sigma ut or sigma y term I mean gets equated to 0. So according to Soderbergh's equation, but for ductile material we use Soderbergh's equation. So Soderbergh's equation is sigma mean upon sigma y, that is yield strength, plus sigma variable upon endurance strength is equal to 1 by n. So this is sigma mean will be 0, and this term gets equated to 0 then, and this will be 50. Sigma variable will be 50 because 50 minus of minus 50 by 2, that is 50 megapascal. Okay, and endurance strength is 100 megapascal, so that leaves us with n is equal to 2. Okay, the factor of safety is 2. Okay, let's move on to the next question. A bar is subjected to a combination of steady load of 60 kilonewton, a steady load of 60 kilonewton, okay, and a load fluctuating between minus 10 kilonewton and 90 kilonewton. Okay, so there is a load that is fluctuating between minus 10 kilonewton and 90 kilonewton, and there is a steady load of 60 kilonewton that is acting along. The corrected endurance limit is given, the yield strength is given, and the ultimate strength is also given. The bar section is square with side A. If the factor of safety is 2, the value of A in mm, you have to fill the answer in mm, so be careful, and according to the modified Goodman's criteria. Great. So steady load is equal to 60 kilonewton, this is given, and fluctuating load is equal to minus 10 kilonewton to 90 kilonewton. So this is the maximum value of fluctuating load, and minus 10 kilonewton is the minimum value of fluctuating load. So if we see that overall maximum load will be 90 kilonewton plus 60 kilonewton, okay, that is 150 kilonewton, and overall minimum load will be, because this 60 is acting all the way along with this fluctuating load, so minimum load will be minus 10 plus 60 kilonewton, that is 50 kilonewton. Now we can find out minimum mean stress and the variable stress from this data. From these two data I found out maximum and minimum load, and from this data I can find out sigma mean, sigma variable and sigma variable, because these values will be used in the modified Goodman's equation. Okay, so from this will be actually, okay, so Goodman's equation is sigma mean upon sigma ut, that is ultimate strength, plus sigma variable upon sigma e, that is endurance strength, is equal to 1 by n. Okay, now we can find out mean load and variable load from this data. Okay, and mean load will be equal to 150 plus 50 upon 2. Okay, this will be 200 upon 2, that is 100 kilonewton, and this gives me the mean stress is equal to 100 into 10 raised to power 3 Newton upon, it is a square cross section with side A, so that is area is A square. Okay, so this is actually Newton per meter square. Okay, so whatever we'll be getting the value of A, that will be in meters, but here we have to fill the answer in mm, so be careful. Okay, so variable load will be 150 minus 50 upon 2, that is 100 upon 2, that is 50 kilonewton, and which gives me variable stress is equal to 50 into 10 raised to power 3 Newton upon area is A square, that is Newton per meter square. Okay, so put these value here and get your answer, that is 100 into 10 to the power 3 upon A square, and sigma ut is 600 megapascal. Okay, so that means you have to put the value in Newton per meter square only. Okay, so that is 600 into 10 to the power 6 Newton per meter square. Okay, so sigma mean is in Newton per meter square and sigma ut is also in Newton per meter square now, plus sigma v is 50 into 10 to the power 3 upon A square into endurance strength is 150 megapascal, that is 150 into 10 to the power 6. Okay, is equal to 1 by 2. Okay, so this gets cancelled out, 10 to the power 3, this gets cancelled out, 10 to the power 3, and this 1 by 6, 1 by 3. Solve it, you will be getting your answer as A square will be equal to 10 raised to power minus 3 meter square, and which will give me A is equal to 0.03162 meters, and we have to fill the answer in mm, so that implies A is equal to 31.62 mm. Okay, so 31.62 mm. So there is a probability of committing some silly mistakes while balancing the units or finding this value of A. So please be careful while solving this question. This was a very nice question. Okay, thank you.